I hope all of you are doing well. Thank you for joining me. In this video, we are looking here at a very interesting function, minus infinity to infinity, hyperbolic secant x, area below the curve, but we will do it with double integrals. When you're looking at these type 1 improper integrals, you will realize it is better to do an initial dy and then a dx. It just is, and I'll show you why. The graph is something like this, 0, 1, y-intercept, then it's going here in the direction of positive and minus infinity towards a horizontal asymptote, your x-axis. That's all what we're looking at. Limit as t approaches minus infinity, the function will approach 0. Limit as t approaches positive infinity, or x values approach positive infinity, your function will approach a horizontal asymptote and your output is 0. Y equals 0 is your horizontal asymptote. This is what we're looking at. If you are doing initially with respect to dx and then dy, that's hard. You can split everything because it's an even function, and you can do just examine here 0 to infinity and then multiplied by 2. But if you're doing initially dx with respect to dy, it's hard, and I'll tell you why. Your lower limit is 0, your upper limit is infinity, but you're tracking along the curve. Therefore, you must bring the effect of that curve or the function into your limit. And since you're going from dx to dy, you must write your equation in the x equals format. X will be equal to inverse hyperbolic. And that right there is our problem. You'll have inverse hyperbolic function to integrate, which is hard. Complete this with your dy from 0 to 1. Dealing with this is hard because this function will come in place of an integrand and its antiderivative. I'd rather not deal with that. You would put a 2 over here to account for that. But I will rather do this in this manner, dy first and then dx. How will that work? I'm going to do a dy integral with respect to dx, and that's easy. Lower limit 0, upper limit is a 1, but you'll track down the curve as the lower limit will go straight, but the upper limit will track the curve. Here, since you're eventually going with respect to dx, you can do y equals format as your upper limit, and it exactly is that, hyperbolic secant x. And then you'll go eventually with dx from 0 up to infinity, and you can put infinity here, or you can do a limit as t approaches infinity, and you can bring a t over here, and then you can bring a 2 at the very beginning to account for that. Now the antiderivative is much easier, or I'm more familiar with this, so I'd rather do it this way. Antiderivative y, upper limit, lower limit, you're just going to get here this becoming the integrand for your next integral. Limit as t approaches infinity, I have 0 to t hyperbolic secant x dx. The antiderivative of this is interesting. 2, limit as t approaches infinity, it's going to be inverse tan of sine hx. I'm looking at everything here from an upper limit t to a lower limit 0. It's not hard. So what is it that we're looking at? We're looking at this 2 inverse tan hyperbolic sine of t minus inverse tan hyperbolic sine of 0. That's what we have. Hyperbolic sine of infinity is infinity, but inverse tan of infinity is a pi over 2, because if you look at the arctan function curve, it looks something like this. As your values approach positive infinity, your function approaches a pi over 2 horizontal asymptote. So you're getting a 2 times inverse tan of infinity, which is a pi over 2, minus hyperbolic sine of a 0 is a 0, inverse tan of 0 is a 0 because it goes to the origin, and this is what you have. Pi is your answer. This entire area is pi. From here to here, it's obviously a pi over 2, but all the way from infinity to minus infinity, it's a pi. Because I have this times 2, I was only focusing here, but I've gotten the end result for all the way here, minus infinity to infinity, and the computations here are good. When you're doing improper integrals, it's easier to do initial dy and eventual dx. That's my experience. Thank you. Have a good day.